is you're only getting the binary you attach to. Now, in ollie-dump, you can configure it to dump more of the range, but you're not getting it separated out in a file. It's not unique. It's put in one place. So you're really only getting the binary you attach to, which may, if you're looking at, for example, a process that you think has been injected, getting the binary is not what you're curious about. You actually want that DLL that may have been injected. So you're missing something with traditional process acquisition. Also, the other thing that you're going to run into is detection of detecting your, there's a monster. Detecting that you're being debugged right now is quite easy. I put a link up there, OpenRCE. It is actually just a reference library of where you can different methods to determine your process is being debugged. And if you can preventing debug can prevent process acquisition, and that is a fail point. That is unacceptable. It's too easy to do process debugging detection. So that is another reason why we're going to build up this new solution. So this new approach, I'm going to break it down to you how we implemented it. You're going to get all the information. Remember I said that the first requirement was access to live physical memory or access to physical memory. So we've covered that. We told you that we go the software method, device, physical memory, object. We've got that covered. The next thing we need to do is find all the processes in memory. Because the way we work is we ask the user, what process do you want to acquire? And then we have to go find that process. So if FU2 is running on the system, then we got to find that process, even if it's being hidden. So basically, processes are represented by eProcess blocks in the kernel. So every process has a corresponding eProcess block. This is an unchangeable feature. If the process doesn't have an eProcess block, the Windows manager isn't going to know about it. It's not going to necessarily get scheduled CPU time. It's going to be a big problem, and you may just see your machine blue screening. So it's pretty safe to say that every process has an eProcess block. With that said, we know that there are certain characteristics of the eProcess block that can't be changed. By changing them, Windows may kill the process. Windows may stop the process from executing. It may still be in memory. You may still see it in your task manager. One example was, but it was not getting any CPU time, so it's not actually executing. So changes to certain characteristics of the eProcess block will hurt the process that you're trying to hide. So we look for those characteristics that can't be hid, and we do this by scanning every memory page. When we map that memory page, we look for these characteristics. And using this method of scanning, we're able to determine all the processes running on the system, hidden or unhidden. With that said, we have a caveat. The method's good. It's a little too good, and Windows doesn't do a good job cleaning up after itself. We've found processes after reboot, dead processes after reboot. You're not guaranteed that the process you found is still running. So you need a good method to eliminate processes that have been exited, and you have a high number of false positives in memory. The characteristics I talked about are not big enough to eliminate all of memory. So you'll find the characteristics in dead memory, in garbage memory, uninitialized memory may look like an eProcess block. So you need a good method to eliminate those as well. I'm not going to dive into the actual characteristic elimination, things like that. That's all public knowledge. If you just Google it, I want to stay with the scope of this and try to get the demos in. But there's a link to one paper we gave about process detection that went a little more in depth than I did. But basically, we now have an ability, using this knowledge, to find all the processes on the system. Every process address space needs to be managed by Windows, because what happens is Windows is going to load DLLs, executables in your virtual address space. And it needs to know what's available. So if you execute a new thread, that thread's going to need a new stack. And that stack, Windows is going to have to know where to put that stack in your virtual address range. And it doesn't use contiguous addresses. So basically, Windows might put your main executable at 4000, and then might put a DLL at 77 something, and then might put a stack at 001C, and it needs to know what else is available for it to use. So the memory sections are just blocks of memory that Windows knows about. So we need to, when I said what the requirements were, we said physical memory, access to physical memory, determining all the processes, and then being able to find all the memory sections the process owns. So Windows does a really good job managing all these sections, and what that means is we can do a really good job doing full process reconstruction, because we can just pretend like we can parse the management it's doing. So what we have here is every eProcess has a VAD root. So we're going to scan for our eProcess blocks. We're going to find the eProcess we want to acquire, and we're going to go to the VAD root. The VAD root is a pointer to a tree. This is a self-balancing binary tree. This tree contains what the structure is actually called in the kernel MMVAD, which stands for Memory Manager Virtual Address Descriptor. This tree contains a self-balancing entries of these. If we parse Well, first off, each of these MMVAD structures contains information we need. It's going to contain the virtual start address, the size of the memory section. It's also going to contain things like flags about the memory sections. Once for every memory section we parse, we write that to disk as a separate file. So you're going to have your stacks, your heaps all written to disk in separate files, which is very easy to use. You're going to have your memory sections that contain DLLs and executables named, and we'll talk about that in a second. So basically, just to rehash, you find all the processes, you find the process you want to acquire, you then parse the VAD root, which is a self-balancing tree that contains Windows memory management information that we can then use for our own good. All right, so the VAD structure looks like this. And then the ones in bold are the ones I'm going to talk about. The starting VPN is the starting virtual address of that memory section. The ending VPN is not the ending virtual address. It is the size of the memory section. Parent is the parent pointer in the tree. Left and right are their children. Pretty basic. U is the flag, so we can bit mask out and figure out, okay, this memory section is execute write, execute read write, execute write copy. We can determine all that. The control area is a pointer to a structure that actually contains the name of the memory section. So if SVC host is the process we're acquiring, its memory section, the memory section that contains the svc host.exe executable is actually going to have the name SVC host with its full path, which is very useful information and allows us to give the end user very useful information about what was acquired. So just to help, because this may be a newer concept, basically I attached to calc.exe with the ollie debug, and then I did alt-m, which is the memory map view. Is it possible to see this? Every address, it's a little small, I think, but every line in there is a different memory section. So the first address you see is 10,000 hex. That's one memory section entry. It's one entry in the VAD root tree. The next is 20,000 hex, 30,000 hex, and then you see 7B. So you see the addresses between there are unused, and Windows is able to know that and then use that information. So that's why it needs to keep track. It needs to know, all right, I can put a thread stack there. I can do something. I can put, if they load a library, I can stick it in there. I can relocate it. So that's all very important information. A common question we got when we first started throwing this around is it safe to assume that the attacker has not modified the VAD tree? And yes, it is relatively safe to assume that. We actually tried to write our own rootkit to remove a VAD entry we want hidden. So like, let's say you inject a DLL and you have a rootkit running as well. That rootkit's going to remove the injected DLL's memory section so Windows doesn't know about it. That blue screens the box guaranteed pretty much, because what happens is it's a self-balancing tree. It's missing an entry. It tries to balance itself out, and it just completely chokes. And rightfully so. There are other modifications that could be made to make it a little harder. In tests, the integrity checking of the VAD root is actually quite good by Windows, and is helpful in ensuring that you're getting what you think you're getting. And I've got a link there to an open source VAD parser. The VAD parsing is not a new thing. We didn't develop it. There's an open source Python script that is able to parse out of memory dumps VADs. So that's the new approach that we have. But there's one caveat that we like to be checked for. And basically, if the memory section is a stack or a heap, it's not going to have a PE header in it. So what we're going to do is we're essentially just going to, the way it works is we say virtual address start, virtual address end, dump it all to disk. If for some reason we can't map some virtual address, it's paged to disk and it's backed by itself, or we're parsing a memory dump and it was paged out at the time, we just write 496 bytes of no ops, or 90s. And that way we keep the file size aligned and we keep everything aligned. So if you were going to incorporate disassembly with some reference on the heap, you can use IDA to do that, and everything's aligned so your offsets are right. But if the memory section is a PE file, we're going to treat it a little bit differently. We don't do section fix-up. We refuse to because of a story I'll tell you in a couple slides. But what we will do is we'll take the same dump. We'll start from the beginning and the end, but we make one modification before we make that dump. Or we make a couple modifications. We go through each section header. For every pointer to raw data and size of raw data, we set those equal to the virtual address and the virtual size after we've page aligned the virtual size like the Windows loader. So we modify what those PE headers point to, and that helps IDA, because what we were seeing was we dump a binary, but it was page aligned, so it was a lot larger than it was on disk. IDA would rightly look at the relative offset, and it would see a bunch of 90 or a bunch of zeros at the time, and it would try to disassemble that. Sometimes it would succeed, sometimes it would have some troubles. So we help it along by fixing up the pointers. And like I said, this allows us to stick and idle a lot easier and makes things a little easier for us. So that's the change. That's the only change we make. We don't do any section fix-ups, things like that. We just change what the pointers point to so that they're easier to see because the binary is page aligned. Now I'm just going to talk to you real quick about the Windows PE loader. Basically, what we need to understand is that when an executable is loaded into memory, it's page aligned. So if you have a file on disk, the first 124 bytes or hex 400, and we're talking non-packed, non-themited, non-anything binary, just your calc.exe, is going to be the PE header, usually. What this means is that with page alignment, on disk, you'd go to offset hex 400, and the text section would start. The text section would start. But with page alignment, what happens is Windows loads the PE header at, for example, the base of 01000, and then it loads the text section starting at 01001000 instead of loading it at 10004000. And this is page alignment, memory alignment sort of work. One interesting characteristic we found is that the Windows loader is ignoring the size of raw data field. So it's actually going to say, well, there shouldn't be anything after here. I need to page align it, so I'm just going to load it into memory. And the loader page aligns all that stuff. A problem that we ran into is that if process acquisition were to rely on the size of raw data for each section, it could potentially miss maliciously inserted data. So we don't, and we actually we mimic the Windows loader in how we align the virtual sizes to make sure we get everything in memory. So I told you I had a story for you. This is from a high-profile target, some malware we found. So basically what these authors did, which was a pretty unique solution, they said, we're not going to write a registry key. We're going to find a system process that's guaranteed to boot up, for example, your SVC host, your services. We're going to then look at a DLL that it imports. We're going to find a DLL entry point that we can modify. So they found a DLL that they thought they could modify. They then overwrote 8 bytes of the DLL. These 8 bytes they overwrote a call with another call. What they did was after they overwrote the call, they inserted malicious code after the relative section size. So after the size of the section, they put their malicious code. When the DLL was loaded in memory, because it ignored the raw size of raw data, the section size, it loaded this malicious code into memory. The call succeeded. The malicious code that they inserted actually loaded another DLL. This DLL had the backdoor functionality that was needed for the attacker to keep control of the system. And that is how they stayed persistent. No registry keys, no modification of the IAT. Just a quick little overwrite. And they took advantage of the fact that Windows page aligns and uses that page alignment from the disk. So it's a problem, and we're seeing it in malware a little bit. So that's the story of why we don't do section fix-up, things like that. We sort of try to take the most virgin look we can at the actual binary. So we got to a point where we had this solution, but the file size for a binary that you acquire in memory is going to be different from that you acquire on disk, or from that's on disk. So we used bindiff to compare what's in memory to what's on disk, and we were able to verify that our approach was successful and that we were acquiring the right amount of binary. We weren't messing it up. So that was how we verified that what we were doing was correct. So real quick, I'm just going to say, tying it all together, scan the kernel memory looking for all processes, parse the memory sections for each process, dump each memory section to a separate file on disk. Pretty simple stuff when you think about it. So what are the benefits? The benefits are quite numerous. By parsing physical memory and not doing the virtual address stuff and having access to live physical memory, we can dump all the executables, DLLs, stacks, heaps, everything that can be useful in reconstructing what might have happened with that process. We also can bypass any anti-debugging techniques. We're not attaching. The process has no clue that we're touching physical memory. So it's pretty safe to say that you're gonna have to actually look for our process name and kill us off and have pretty process-specific attacks to subvert us. Recently, Day1-Track1-Peter released a rootkit that used debug registers or trap referencing to hide a virtual address range. Because we don't access virtual addresses, we go virtual address to physical memory, and we don't ever read from the virtual address. We only read from physical memory. This type of rootkit doesn't work on us, and that's a good point to make. The other thing is, if you have an injected DLL that's only on disk, for example, Metasploit has something called Meterpreter that loads a DLL off the wire into memory without ever putting it on disk. It patches the window, it patches the load library, I believe.